Oh, cute. Cute. All right. This is the last thing of this really long chapter 4. We start trigonometry next. We're doing a full course in trigonometry. I love it, so I'm excited for it. Get to do some pretty interesting stuff. It's math. All right. We are using these calculators today. I need you to practice with me when we're doing these because we are using the calculators today to create regression models. Regression is where we find a line of best fit, okay? And your calculator, we would do this way down in algebra where we'd have maybe a bunch of data points like this, all right? We see a positive correlation, and then what the calculator does is it can find a line of best fit that goes between all those data points and approximates the relationship, okay? And it uses a crazy formula that basically takes distances between values and tries to minimize all those little distances between all those data points. So we're doing the same sort of thing today. We're using our calculator to find regression models of all these different function types that we have been working with, okay? So we use the shape of the data to determine which regression model is used, and we have these that we're looking at today, the exponential model. What does the exponential model look like? What do I call it? I call it the Superman. Yeah, it's the Superman to the moon graph. And so that if our data fits this sort of curvature, then this would be sort of an exponential model. The nice thing is she's going to tell us what model to use here to fit our data to. The power model, well, that's like ax squared or ax cubed or ax to the 4th, something to the 5th, okay? Those are just powers. I don't know why she has it drawn that way. I don't know why she has it drawn that way. She has it drawn like this, but I don't quite, I don't know why she would draw it like that. I would think it would be more like this, but I don't know. I don't know. It's just usually we don't have data on the other side, so there'd usually just be one side to that thing. So maybe that's what she's talking about. We don't usually see the one side of the data because we don't usually have negative data points. But that would be like 2x squared or 3x to the 4th or something like that. So it's like a parabola shape, okay? And then our logistic model, so that's our basic setup, a basic formula for a logistics curve. And logistics curves work really well to model actual population growth where there is this, it starts to even out again at the top. There's some horizontal asymptote there where it sort of reaches the maximum density of our lake population. And then we have logarithmic. What's the log ride look like? Up, and then over, yeah? All right, it was the boring log ride. So it looks something like that. It has that vertical asymptote, and it grows really, really slowly. So these are the different types of models that we're looking at today, and they're going to tell us how to use them using our calculator. So the population of a city in thousands from 1995 through 2000 is shown to the left. So here is our data. And we want to use an exponential regression to write an equation to model the data. So the calculator is going to do that for us, which is kind of nice. And then we have to solve the problem. So this is what we did yesterday. Find the year in which the population will reach 80,000 people. So what we're going to do is we're going to learn how to put all this stuff into our calculators. And the nice thing about using years is that I can reset them to whatever I want. So I'm going to just, instead of having to type in 1995, can I just call it 0? Yeah. And then in which case 1996 would be 1 year later, and 1997 would be 2 years later, and 1998, 3, 4, and 5. So that's the nice thing about time is we can reset it so that we don't have to type in all 4 digits, because that would be forever. So first things first, on your calculator, step number 1, so you can do this later, you're going to go to the Stat menu. Stat stands for statistics. Yes, it stands for statistics. And we're going to choose Edit, because we're going to edit our statistics and enter the data. So on your calculator, we are going to go to the Stat menu, which is right here below the delete button. Are you with me? Stat. You get this menu. Got it? All right, and then we're going to choose number 1 because we want to edit it. So choose number 1. And you get your 2 lists. Do you see at the top list 1 and list 2? Do they say L1 and L2? Let me know if they don't. Yeah. Stat and then number 1. All right, so you're going to enter in your data. You're going to enter in 0, 1, 2, 3, 4, 5 in list 1, and you're going to enter the populations in list 2. You need to tell me now if your calculator does not say list 1 and list 2. Okay. All right. I'll give you a second to get the data in. All right, I see. You're done? Almost done? Now, if your data doesn't match, you're going to have an issue. Okay.
Wow, it's just adding.
Yeah. Okay. All right. Are you good? Okay, now that the calculator has the data, we are going to go back to the Stat menu. That was Enter Data. All right. Then the second step is to go back to Stat. But now we're going to go to the Calculate menu. We're going to go to the Calculate menu, and we are going to choose the regression that we are being told to pick.
Oh, wait. We did this last.
Probably. So we want to do an exponential regression for this problem. And so I'm going to go back to Stat. And arrow over to Calculate, we want exponential regression. So we're going to scroll down. Oh, right there, XReg is number 0, is exponential regression. And so we're going to choose that 0. And you can see that it's saying our X data comes from list 1, our Y data comes from list 2. And all you have to do is basically hit enter. Enter, 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 and enter, and then it'll finally calculate for you. Okay? And then it gives you an equation. And so this equation is the form y equals a times b to the x power. And I can plug in my values, and I think we're going to just round to 2 decimal places here. So the a I have is 54.7. And the b is 1.01 to the x power. All right, so there's our little model. And this is giving, what does our y variable actually represent in this equation? Well, yeah, it's the population. And we want to know when it reaches 80,000. So we're going to solve the model. This is what we did yesterday. Now that we have a model, we want to know when will that population reach 80,000. So we want to know 80,000. Oh, wait a minute. Should I use 80,000? So, but the population of a city in thousands. Just use 80. Yeah. We have to be careful. This 54.7 isn't 54 people. It's 54,000 people, okay? So it's really important that we're paying attention to what we're talking about. So that initial amount of people isn't just 54, it's 54,000. So we want to know when it reaches 80. 1,000 people, all right? So when 80 equals 54.7 times 1.01 to the x power, and that's really a t for time. What do we do first?
Divide by 50.
Divide by 54.7?
Yep.
Divide by 54.7. Okay, so let's see. 80 divided by 54.7, some crazy thing, 1.46 equals 1.01 to the x. And then what should we do? Natural log, both sides. The nice thing is we have this decimal running in our calculator, so I'm just going to keep using it. My power is going to drop down in front, so I have the natural log of 1.46 equals x times the natural log of 1.01. And then what do we need to do? Divide by the natural log of 1.01. So I'm going to take my answer, I'm going to do natural log of my, natural log of my answer, and then divided by the natural log of 1.01. Yeah, and we get x equals 38.2. 38.2, what were we trying to find? The years, 38.2 years. So is this year 38? What does that really mean?
38 years plus. So 2038. No, this is starting in 95. 1995.
Starting from 1995.
And you add 38.2.
Yeah, so starting in 1995, and we're adding 38 years.
2033.
So,
During this year.
yeah.
So, dude, that's only 7 years away. Yeah. That's only 7 years away.
You add the 38 to the 2000?
Yeah, why? Because it gives you up to 2000.
No, because this is when we're saying that our time is 0 here.
Okay.
Yeah, and
okay.
Yeah, so we would want to add. All right, great. Let's do another one. The body weight in pounds and the pulse rate in beats per minute of a group of animals is shown to the left. Use the power regression to write. So there's the regression model we're going to use to write an equation to model the data and estimate the pulse rate in of a 225-pound animal. So here we're entering the data. This is going to be our X data and our Y data, so that's kind of important to know. So we need to go back to stat and edit, and I'm going to show you how to clear your list. Yeah, you highlight the L1 and do clear and enter, and it clears all the data. So highlight L2 and do clear and enter, and it'll clear the whole list for you. Please do not delete L1. Okay, clear and enter. All right, so then you can enter your data. Oops.
Good job. No, what do you want me to say? I know. Yeah, you're too good. Yeah. You should be able to. You should be like in upper math. Very smart. What if Sasha was just a genius and I don't even know? Are you a genius?
All right, did you get your list data in?
Yeah.
You good? Okay, then what do we do? Stat, calculate, and we want power regression. This is a different one. It says use a power regression. It's letter A. Letter A is the power regression. And then enter, 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 enter. And so we get y equals 296 point, I'm going to go 0.1, I guess, times x to the negative 0.29 power. All right, so we want to know, now, from our table, I know that my X is representing the weight of something, and the Y is representing the pulse of my animal, okay? And so it says, estimate the pulse rate of a 225-pound animal. So where does the 225? Yeah, 225 goes in place of the X. So we have 296.01, and we're plugging in the 225 pounds, the negative 0.29 power. So that's just plug it straight in. 296.01, plug in 225 to the negative 0.29 power. So I'm just plugging it straight in. No solving required, just evaluating. 61.54. And that was the pulse rate. So that's the pulse rate in beats per minute. Taryn, you need glasses on? It's pretty squinty. All right. All right. Questions on that? Okay. All right. Let's look at the number 3. The table to the left shows the temperature each minute after an oven is set. Use logistic regression to write an equation to model the data, and then estimate the time it'll take for the oven to reach a temperature of 425. So again, with my table set up like this, X is minutes and Y is going to be the temperature of our oven. So again, I'm going to go back to Stat and Edit and clear my list. So highlight L1, do clear and enter. Highlight L2 and do clear and enter, and then you're good to go. All right, did you get your data entered?
Yep.
All right. And then we want to go back to Stat and calculate which one? Logistic is letter B, logistic equation. Enter. Oh, I think I killed it.
You can't
enter
too many.
Yeah.
And then you gotta wait and let it load.
All right, so what does this mean, this crazy expression?
C over all that.
Yeah, so it looks like what we started with at the top of the page. That's what it really would look like if it was in a fraction format. All right, so we get y equals C, 478.25 over 1 plus our A, 7.01 times E to the, oh, that's opposite of B, so negative 0.2, do we? Yeah, I'm going to round that to, because it's 0.297, I'm going to round it to a 3. 0.3 x. So I'm rounding that 0.29 to a 3. So 0.3x. All right. Now, x represented the minutes, and y represented the temperature. So we want to estimate the time it'll take the oven to reach a temperature of 425 degrees. Where does that 425 go? In place of y. Good. All right, so we have 425 equals 478.25 over 1 plus 7.01 e to the negative 0.3x. All right, what do we have to do? And then divide the 425, right? Okay, I have to do a little crisscross action here. 1 plus 7.01 e to the negative 0.3x, and then I would divide by the 425 eventually, so 478.25 over 425. Are you okay with that? Yeah, a little crisscross action there? All right. I'm going to go ahead on my calculator. I'm going to type that in, 478.25 divided by 425. That gives me some crazy decimal. What am I going to do next? Oh, wait. Minus the 1. I'm going to subtract 1. So I would have 7.01 e to the negative 0.3x. And my fraction, I'm going to subtract 1. That gives me 0.125. Yada, yada, yada. Are you with me?
Yeah.
Okay. Then what should we do? Divide by 7.01. So I'm going to just go ahead and divide by 7.01. And I get e to the negative 0.3x equals 0.0178. I don't know. I cannot just have 2 decimal places. It's so inaccurate. Okay. And then what should we do? Natural log. I'm going to take a natural log of both sides, and my power is going to drop in front. What happens to the natural log of e?
1.
It's 1, so that goes away. So I get negative 0.3x equals the natural log of that. I'm going to go ahead and do natural log of my answer so that I'm pulling in that whole decimal. And I get negative 4.024. And then I need to divide by negative 0.3. So divide by negative 0.3. X equals 13.4 minutes. Isn't that fun?
Yeah.
Super fun, right?
Oh, that's so cool.
Okay. I think that's all I think I need to do, really. No, it's a worksheet.
Once you get down to here, our models, but it's...
Yeah, I don't think.
We're gonna choose the best model?
Well,
I already know how to do that.
you already know how do you choose the best model?
The one closest to 1, not just ours to last year.
All right. So, choosing the best model, there is only the one. Oh, there's 2 at the bottom. Okay, I guess I will talk quickly about that. So, R is the correlation coefficient, all right? And so on, it looks like a couple of these, you're going to get an R value. I haven't done this in like forever, so there's an R value right here. And the closer you are to 1 is the more accurate it is to the actual data, all right? So it's the closer you are to 1 or negative 1, that's going to be the better model. So choose the one that has the R value closest to 1 or negative 1, all right? You'd sort of run both and see which one has the better R value. I think you'll be able to get it. Yeah? Okay. All right, cool. I think that'll do.